Okay, welcome back, class, to part 2 of week number 9 on machine learning. It is a rainy, cloudy day today, and I thought, what a great time to talk about machine learning. Usually days like this, I reserve for things like reading seminal papers in the field, going back to my batch of research papers that I have stacked up, and so I enjoy those. And sometimes I take out my ESL book and I refresh myself on a number of interesting topics on machine learning. So today I'm going to be talking to all of you about machine learning, supervised machine learning, specifically the R code that we have to discuss. So before we get started, one important announcement that I posted on Canvas yesterday, and that is I managed to get UCLA Extension Administration to give us a few more extra days to turn in our coursework for this quarter. So I had originally said that the last date for coursework would be March 21. And now it is March 26th. So some extra cushion there in case you're running short on time. Hopefully that helps everybody concerned. So with that, we can get started with the code. Last lecture, or part 1 of this lecture, which is available as a video on Canvas, covered some intro material as well as all of the slides. So there were a lot of slides for this topic. I guess they were needed because there's a lot of very critical topics to discuss with respect to supervised machine learning. And so we managed to cover all the slides. Usually I don't cover all the slides at once, but because it's kind of exhausting after a while, but because I planned to break up the lecture into 2 pieces, I decided to do it that way. So at this point, you have all of the sort of conceptual perspectives on machine learning. And now we're going to dig into the code that will implement those concepts. Now, the good thing about this code module for this week is that this code will be instrumental for you to move forward with data science in the future. So this code will become a very integral part of your data science toolbox. So when you get a new project in the future, instead of having to remember syntax and having to research, different coding procedures, all you have to do is dig into this code module, because there's many pieces here that you simply have to copy and paste and then configure for your new purposes. So that's what I hope for you, is that you're not going to be spinning your wheels after this class trying to figure out how to get started. You're going to have a base of code that you can really get serious work done with. So anyway, yeah, that's why it's important for us to go step by step through this code module, because it has important code chunks, code snippets. Okay, so here's the code. We are going to be using a number of packages and data sets in this demonstration. One of the packages we hadn't seen before, it's this one called using R. It has a number of useful data sets, and it was published as part of a popular book called Using R for Introductory Statistics. And in the book, there's many R code examples, and so the author had to produce all of these useful data sets. So they're small little toy data sets like we've been using. And so we're going to be using some of that. So let's bring that into memory. Okay. And then we'll be using, let's see, to start off with, for our initial demo on this topic, we're going to be using the Galton data set, which is that it's a very simple data set that is very well known in the statistical circles. It goes back decades, and it is a data set that just had 2 variables and 928 rows. 2 variables. It's basically the height of a parent and the height of the parent's child. Okay, so the theory is, and we're going to explore this, is there a way to use machine learning to predict the height of the child, knowing the height of the parent? It seems reasonable hypothesis. So let's see how well that does. So to do this, we're going to use a simple linear regression. Now we're using regression because the response variable, the thing we're trying to predict, namely child height, is numeric. And we're using simple regression, that is one predictor, because the predictor variable is parent height. So we have child height, we're trying to predict parent height, we're going to use to predict width, and that's a perfect scenario for simple regression. So the first thing we're going to do is we're going to plot the response versus predictor and see what the plot looks like. Okay. And let me just extend this out. Okay, so here's what the plot looks like. And this is the kind of thing we typically do when we're exploring regression early on, is we want to see a scatter plot that will tell us whether we see any trend with respect to the response and the predictor. So here on the x-axis, we have parent height. On the y-axis, we have child height. And then all the blue data points in between constitute the data. Okay, so we see the data is somewhat discrete because there are values that are sort of stacked, both row-wise and column-wise, probably because the data was collected via survey, and so the respondent just had certain choices they can choose, not just any old height value, and so that's why the values are discrete. But aside from that, we do see there's possibly a gentle pattern that we're looking for, meaning that for any incremental height for parent, we see an incremental increase in height for child. So it starts off at the origin and it goes upwardly toward the upper right corner of the scatter plot. So, but there's not a really definite trend here because we're looking at a lot of cloud of data points. But this is often the case that we're confronted with when we deal with regression, and we just have to use regression methods to do the best we can with respect to finding the regression line, okay, and establishing a set of predicted data points. Okay, so here we have our first little experiment. Now, the next thing we're going to do is we're going to fit a linear model. So we call the LM, the linear regression algorithm in R. And the way we define or configure the model is using what we call a formula syntax. So the formula syntax is very simple, and fortunately, it's the same syntax for pretty much every algorithm in R. And this is one of the things I really like about R so much is that you can repurpose this formula syntax for anything. And that's not the case with other data science languages. So I really appreciate that. It's like a no-brainer. Let me describe what it is. So on the left side of the formula, you have the response variable. It's always on the left. So I'm specifying Galton $child. That's what we're trying to predict. Then we have a little tilde. And then on the right side of the tilde, we have the predictor, or we'll see later, multiple predictors. So in this case, our predictor is simply parent. And that's the setup that I described before we started this example. So that's what we're trying to do. So let's see what happens when I run this statement. Okay, so R has asked the LM algorithm to fit the model based on the formula. And now what happens is I have a new object called LM1. And notice it's a list of 12 items, a list of 12 items. So that means that the algorithm seemingly did a lot of calculation very quickly. And so it stored the results of the calculation in a list object. And so we're going to explore that list object in a moment. Okay, so one of the things in the list object was a item called fitted. See right here. So I reference it LM1 $fitted. So I'm extracting the fitted information. So what fitted is just another word for predicted. So here is I'm extracting the predicted child heights. That's what running the regression model afforded us. So what I'm doing here is I'm using a base R graphics command called lines, and the way you define a line is you have two coordinates, x and y. And so the first coordinate, x, is parent, which is the same coordinate that I'm using here on my scatter plot. Then the second coordinate is the predicted child height. So let's see what happens when I run this. There we go. The red line is called our regression line because it is showing us that after you do ordinary least squares, statistical process, it says this is the best I can do based on all these data points. This is the best I can do. And when I look at the regression line here, I go, yeah, it kind of makes sense. It's like right through the middle of the distribution of data points. It's not off on one side or at the top or the bottom. It's like running right through it. And it's got a slope. And the slope is something that I told you I recognized in this scatter plot early on. I detected some sort of trend, right? An upward trend. And this regression line captures the essence of that trend. Okay, so this is useful. This is something I always do with regression. Now, there's other stuff that we can do that we have to display and we have to analyze. So every time you run a regression model, you have to analyze the output of that algorithm. And the typical way you do that is you run a summary of the object. So I say summary LM1, and I get all of this stuff. Okay, it's a lot of stuff that it prints. And it kind of looks complicated right now, but you're going to see this over and over and over again. It's going to become really second nature to you, guarantee it. But for now, let me just point out some highlights. And these are summarized in the comments here. So first of all, in this, there's this section here, it's a coefficients matrix. And in the matrix, there's the first column is called estimate. So these are the estimated coefficients that were calculated by ordinary least squares. And because this is simple regression, I only have two coefficients. One is the intercept value, y-intercept value, and the other is the slope of the line. So, so these two values here, 23.9 and 0.6, those are your coefficients. Now, these are like the most important result of the algorithm calculations, because the coefficients are what you use to make predictions in the future. Okay, so we'll see that. Another thing I want to point out is the p-value column. So if you look also in the coefficients matrix, there's this column, which has two numeric values, and that's called the p-value column. So p-values, well, the one you're really interested in is this one, the p-value associated with the predictor. The p-value indicates how predictive this feature variable is toward the prediction of the response variable. So it says, how predictive is parent height to predicting child height? And what you're looking for here is the smallest value possible. And then this one is a pretty darn small value. It's 2 times 10 to the minus 16. So that's tiny value. And you won't always see a value like this. Sometimes you'll see like, I don't know, 0.06 or, you know, other values. Nothing greater than 1 though. And so you're looking for small values. And that will just indicate to you that this is a good predictor, so that in the future, you can either include or not include the predictor for, for this purpose. The other thing you're looking at is the asterisk column. So it's over here. And here is where R does a nice little assist for you. It'll say this predictor variable offers some level of statistical significance. And you're looking for, like if it's high significance, you're looking for 3 asterisks, maybe not so high, 2 asterisks, maybe just a little significance, 1 asterisk. And if nothing appears here, then that shows no significance. And usually the number of asterisks you see is correlated to the size of the p-value. So a very small p-value will result in a lot of asterisks. And that's what we see here, very small value and 3 asterisks. Okay, so that in a nutshell is what we're looking for. But there's other statistics that are calculated here, which we'll see more of later. But you need to get well acquainted with the summary of a linear model object, because that is the way that you determine how good of a model it is. Now here, if I say names of the linear model object, I get these these 12 elements of the list. So we saw already this one in that lines plot we did. But notice in the lines plot, I only used the word fitted. Yet when I look at the name of the list object, it's called fitted.values. And remember our discussion about abbreviations in R. I said R is very forgiving when you abbreviate stuff. So this is an example of that. I didn't have to say fitted.values. I could have just said fitted. I mean, I could have just said fit and it would have worked. But see, here's my problem with that is people kind of get I mean, they try to be slick with this stuff, and they say, "Oh, I don't need the whole element name. I'll just abbreviate it to my desire." And the problem with that is, people might have come up learning R in a different way, and the way they learned was always fitted values. And so when they see fitted in your code, they might think, "Oh, what's this person know that I don't know? Why is it a different element, or is it a different algorithm? Why is it fitted instead of fitted values?" So I prefer just to do everything formally and just add, just use all of these full names. In the code below, we're going to see I don't do that, but I just kind of reinforcing that you could abbreviate stuff. So in fact, right here, I say LM1 coef instead of coefficients. So here, let me extract this. Let's see, here are those two values I was just showing you in the coefficients matrix a moment ago. So 23.9, 0.6. So these are extracts from the linear model object. And we will use these in a moment. Because what we want to do is we want to use the trained model to make predictions. We trained the model. We determined that based on preliminary review of the model object, it seems like it'll be a good model because the p-value is small and I get 3 asterisks. So I'm not going to look very much beyond that at this point. So I say, well, okay, it's a reasonably trained model. Now let's use it. So what I'm going to do is I'm going to just say, I'm going to use the trained model to predict a child height based on a parent height of 60. Now let's look at data set for a moment. So let's look at parent. So here's parent, and just a quick scan. Yeah, I don't see a parent height of 60. Oh my. Cell phone's going crazy with an emergency alert. I don't know what that's about, but I don't think it'll affect me. Let's do this. Okay, so here's the range of values, 64 and 73, min max. So I'm doing a little experiment here with the linear model. I'm saying, well, if this is a reasonably good model, let's try to make it predict a parent height that it's never seen before, 60. Okay, and so here's the 60. I'm sorry, there's the 60. And this little equation here that I've set up is that that equation that of a line that you've seen, if you remember back to high school algebra, when you were plotting lines on graph paper, y equals mx plus b. So in this case, y is child height, predict child. Mx, m is 60, x is the coefficient value, and then b, the y-intercept is the second coefficient. So I'm pulling these coefficients out of the linear model to use in this formula to predict a new child height. So when I run this, I display it, I say, okay, based on the trained model, I have a child height, I'm sorry, a parent height of 60. My predicted child height will be this, 62.7. Okay. So that's how you use a trained model, is you use the coefficients. And that's why I said that those coefficients are like probably the most important parts of the hold on, I'm just admitting somebody new to the Zoom. Welcome, 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 you hearty souls, to join me on a rainy Friday morning. So, anyway, continuing. We can now look at some other features of R that you can use to take a look at the trained model. So one of the first things we do, so this is like a diagnostic plot. Now, in the slides, I told you about 4 ready-made diagnostic plots, and I'm going to show you those in a moment. But for now, I'm just showing you sort of a makeshift one, a do-it-yourself version of those. So here, I'm going to be showing you what's called a residuals plot. So let me display this. So here's what a residuals plot looks like. So on the x-axis, you want to see the predictor. Yeah, the predictor, parent height. And on the y-axis, you want to see the residuals. So residual is another term for actual versus predicted. So the actual, remember back to our lecture earlier in the week, we're always concerned about how close the actual value is to the predicted value. So we're always worried about that. And so in this case, this graph is showing us, for each of the data points, how close it comes to the predicted data point. The predicted data point is shown on this red line, the 0 level. That means the residual is 0, means the error between actual and predicted is 0. So because we have data points above and below the regression line, we have positive and negative residuals. So that's why we have, the 0 point and then plus residuals and minus residuals. Okay. So as the comments say here, the data points you're hoping is that they should all be centered around the 0 line. And this one is fairly reasonable. I mean, it'd be better if it was closer. But sometimes you don't get that. Okay, So that's a residuals plot. So the example I just showed was very simplistic. It's simplistic because it's only simple regression. There's only one predictor, and it's also simple because I didn't do the typical thing that you do, which I told you we must do in the slides. I said that you have to split the data set into training and test. So I didn't do that on the example I just showed you, but in reality, you should always do that. So now I'm going to show you a more involved example for multiple regression. And this time I'm going to split the data set. So here is a data set I'm going to use called CAR. And I'm going to load a I'm sorry, the package is called CAR. Data set is called Prestige. It is a small data set, 102 by 6. And here is what Prestige is. So it is a data set that has, I don't know, some result of some sort of survey, prestige of Canadian occupations, okay? And so here is the data dictionary. We have, first of all, I'm going to show you the prestige value. So this is some sort of score that offers like a ranking of prestige for an occupation. So this is going to be our response variable. Predictors, well, everything else, you know, an education, income, percentage of incumbents who are women, I'm not sure what that is, census, occupation code, and then a type. It's like a factor variable with 3 levels. BC for blue collar, prof for professional management, and WC for white collar, okay? So that sets the stage. Okay, so we can do a summary on this data set. Let's see, so we have all numerics except for the type variable. And the only variable that has NAs is the type variable. There's 4 NAs. So modest number of NAs. So in this case, I think it's probably okay to just get rid of the NAs instead of doing, you know, any sort of further assessment, you know, NA handling. So we can just pass the whole data frame, prestige, through NA omit. We've seen this function before, and it just removes all the rows with NAs in them. So now we get NA, prestige, no NA. And we can see that the number of rows in this new one is 98 versus 102, so it cleaned out the 4 NA rows. Okay, so that's a little data munging we did. Next thing we do is we split the data set into its training and test parts. So this code here, I'm going to highlight it. You can use over and over again for pretty much any data science project you do in the future, because it will split a data frame into training and test. Now there are like functions you can call from other packages, like the carrot package I mentioned to you few weeks ago. I mean, there's a function that does this for you, but I'm just saying that if you want code that does it and you don't have to think about it, you can just reuse this code. So the way it works is it looks at the data frame, prestige, no NA, grab the number of rows. Then here's where I specify the split of training versus test. So here I'm saying training will be 60%, test will be 40%. And so I multiply it by n, I round it, get an even number. In this case, it becomes 98. I set the seed value because I'm going to use the sample function in a minute. So let me set it. And then I, take n, that's sort of my set of rows that I want to consider taking a sample from. And then I say out of that, I want to take this many out. So n is 98. N train is 59. And so I get this t index. Integer vector, which is 59. So that is basically a list of rows from the data frame that I chose randomly. And so now I can use t-index using simple subsetting to obtain my training set right here. So train prestige now is 59 by 6, same 6 variables. And then I say minus t-index, so I get everything that's not in the training set, I get in the test set. So I get test prestige, and that is 39 by 6. So that's all there is to it, to splitting a data set, or data frame into training and test. So now I'm ready to do a little EDA, data viz EDA. So I want to take a look at how some of the potential predictors correlate with the response variable. Okay, so I take some scatter plots. I'll do one, say I'll plot prestige versus education. See what that looks like. Okay, so I get this scatter plot. Okay, now this is a good one. This is what I often hope to see, because I see a distinct trend. Starting at the origin, moving, upper right corner. And so I can see that this would be useful just by examination. Let's look at prestige versus income. Okay, now this one, not so good. I mean, it looks like there is an upward trend, but then there's some stuff that goes on up here. So it almost looks like there's a nonlinear trend where instead of a straight line, maybe we could fit a curve to these data points. And so I would say that it's not a great fit or correlation, but it's something to consider. Let's look at the third one, plot versus women. Okay, so now that's pretty clear. There's no trend. It's just a bunch of data points, big cloud. So my guess is going to be that the women variable is not good at predicting prestige. Education, definitely. Income, maybe. We'll see. So this is what you go through when you are doing an analysis of an algorithm. Okay, so now let's train the algorithm. So we call LM, and as before, we specify a formula. Now, this is a formula that's a bit different than the simple regression case. So here I say, I indicate the response variable on the left side. Then my little tilde here. Then I have a period. And the period just means to R, it says, I want to use all the other variables as predictors. So you don't have to like list them out one by one. You just say all the rest. And the reason I didn't have to say, you know, train prestige, dollar prestige here is because in my data argument, I say this is where the data is coming from, this data frame, and so I don't have to repeat it. So let's train the model. Let's look at the summary. Okay, the summary, you know, as before, but look at my coefficients table is much bigger because I have more predictors, right? So I have a row for education, a row for income, women, you know, the numeric predictors, and then I have two rows that don't look familiar. There's no variable in prestige called type prof. There's no variable called type WC. So what R did was it said that, okay, you're asking to use a factor variable as a predictor. And so what it does is it creates a sort of a internal default predictor variable, which is for one of the levels. And then it creates two dummy predictors for the other levels. So one level is prof, and the other level is WC. And that's why when you use factor variables, depending on the number of levels, you'll see a number of additional lines in your coefficients matrix. Actually, n-1, where n is the number of levels for the factor. Okay, so now taking a look at this coefficients matrix, I look at the p-values, and I look at the p-value for education, and it's very small. Now, oh, I forgot to tell you, when you're looking for smallness as a p-value, small is anything less than 0.05. And 0.05 is some sort of mythical threshold that some statistician chose years ago, and it's just stuck. Not everybody's happy about that. There's continuing debate on the 0.05 threshold for p-values. I see it everywhere. And even scientists like, you know, like chemists or astrophysicists, I mean, they all use this same stuff. And they all argue about this p-value threshold level. So I'm not going to worry about all that. I'm just saying that's the way we do it. So let's move on. So this one is definitely less than 0.05. 3 times 10 to the minus 5. And I get 3 asterisks, which is good. Here's another p-value. It's 0.0005. So also small. So even though I wasn't quite sure about the income variable, R ordinary least squares says, yeah, it's a pretty good predictor. But look, none of the others are good at all. All these can be sort of ignored because they're not going to be good predicting prestige. So sometimes what you do when you see this, you'll just go back up, and instead of using all predictors, you'll just carve out the ones that are indicated here. And don't worry about the others because they don't help the cause. Okay. So now let's take a look at our some diagnostic plots. So let's look at predicted versus residual plot. So I do a scatter plot. The X and Y coordinates will be coming directly from the linear model. Notice I'm taking from LM2 now. So the fitted, which is the predicted values for the prestige variable, versus residuals, which is the difference between actual and predicted. So let's see what that looks like. Okay, so again, it's a plot where I have a 0 point, and then I have plus values, negative values, and then fitted is on the x-axis, which is, these are just predicted values from the algorithm. So what I'm hoping is that most of the data points sort of center around the 0 line, and I guess for the most part it does that. If I can imagine this 0 line right here running horizontally, then yeah, these other data points in the plot, they sort of center around this 0 line. So this is pretty good. And then another thing you can check, you might as well, you want to see if there's any inadvertent trend based on the row number in the data frame. Because when you get a data set, you don't know how the data is collected. You have no idea any sort of inherent bias in terms of for data collection. So one thing you might want to do is just look at residuals by itself. So these are residuals all by itself, but the x-axis is simply the row number. So if you look at this and you see some sort of weird pattern or cluster or something like that, it might indicate that there was some sort of inherent bias based on, you know, the position of the data point in the data frame, and that's not good. Okay. Yeah, not good. So, but this one shows nothing like that. And let's see, now we're going to use the predict function for the linear model. So every machine learning algorithm has its own predict function. So when you call predict and you pass to it, you know, a linear model object, it says, oh, I'm going to use the predict function for regression. And you simply pass it the trained model as the first argument. And then second argument is you point it to the test set. So what this means is it's going to look at the test set, but it's going to ignore all of the test set's response variable values. It's going to pretend they don't exist. Instead, it's going to use the trained model to predict a new set of response variable values. These are the predictive versions. So now, once you do that, you have predictive versions and the actual versions. And that is how you can determine how good the model is working. So let's do that. And now what I have is this the vector predict 2, and this is what's in that numeric vector. It's a bunch of predicted prestige variable values. And notice that the elements of this vector are named. Oh, that's one thing I should have shown you. Hold on. Prestige. Let's look at the training. So this prestige data set has row names. That's where the names of the professions are. It's not a data column, they're row names. So here are the other numeric variables. Here, prestige, which is our response. Here's our factor variable, so you get the idea. Okay, so now that I have predicted response variable values stored in a vector, I have actual response variable values stored in the test set, I now can compare them. And a great way of comparing them is using our core function, correlation. I can calculate a correlation coefficient for these two vectors. And I will do that. And there it is. And boy, that's highly correlated. 0.9. That's a great correlation. So that means that this model is going to be pretty good, pretty predictive. I can also do a residuals plot. I'm sorry, a QQ plot. So here I'm going to extract the residuals from the LM2 object. I'm doing it a different way. I could have said LM2 $residuals. That's what we saw above. Or I can use this extractor function, residuals, and then, give it the name of the object as an argument. Either way, they both work. So now I have all the residuals, and I can plot them. And so it shows, this plot shows whether the residuals are normally distributed. So a good linear model will have its residuals very close to the straight line, and you can see that they are indeed wrapping on that line. So that's great. So this model is looking better and better. So let's look at one last plot, and this is sort of I don't know, you get to a point where you've checked all the standard data visualizations for determining how good a model it is, and then you, I don't know, think of others. So this is sort of an other type of plot. So here I'm going to plot the actual response variable values from the test set versus the predicted. Okay, versus the predicted. So on the x-axis, I have actual values. On the y-axis, I have predicted values. And here we're trying to see how they sort of match up, pair up. And we see the trend is definitely such that they are pairing up pretty well. And that's why the core value, correlation coefficient value was so high is because it assessed numerically what we're seeing visually here. And the other little nuance here I added was I added a third variable to this plot. I'm doing that PCH trick that I showed you back in week 8. I say PCH equals, I cast to integer the type variable. So remember what happens when you try to cast from factor to type, factor to integer, is the resulting integer values are just the level numbers. So that's reasonable. It's just some way of distinguishing between the level numbers. So here in my plot, I'm getting little open circles, plus signs, and triangles. And here is the legend. So the only reason I'm doing this is to see if there's any sort of pattern, cluster, anything that I can sense. But when I look at this, I see no, I don't really see anything that sticks out. So there's no need for concern. Okay, so now let's look at some numeric measures of model performance. So in the slides, if you remember from the previous Zoom video, I mentioned a couple of statistics, like R squared, another one's RMSE. So let's look at those now. So here, let's look at RMSE first, root mean squared error. And I'm going to define a UDF for you to use for calculating RMSE. So this is another useful thing to place in your data science toolbox. So in statistics terms, RMSE is the standard deviation of the residuals, or the prediction errors. Residuals, as we've discussed, are a measure of how far from the regression line data points are. RMSE is a measure of how spread out the residuals are from the regression line. So in other words, it tells us how concentrated the data is around the line of best fit. And thus, lower values of RMSE that we'll calculate will indicate a better fit of the model. So as an example, if you're predicting home prices, so the response variable value is going to be the price of a home. So it's a large integer number. And the RMSE in this case will indicate how far off your predictions will be in dollars. So the unit of measure is important there. The unit of measure for an RMSE is the same as the unit of measure for your response variable. So for homes, let's say, in hundreds of thousands of dollars, and you calculate an RMSE of $1,000, that's pretty good because it's very small. The error is very small when compared to the response variable values. So here is a UDF to do this calculation. I'm not going to go over the math, but it's pretty easy. It takes two arguments, y hat and y. So y is a variable that you typically call the actual response variable values, and y hat is usually the variable you call for predicted. And so it's just simply a vectorized expression You subtract one vector from another, you square it, and then you calculate the mean of that. Oh, then square root. So you typically will calculate a training set RMSE and an RMSE for the test set. And then you would compare the two. They should be similar. They should be close. So if the RMSE for the test set is much higher than that of the training set, it's likely you've badly overfit the data. So it's an overfit condition. So this is something you will have to be worried about with your class project. You know, you calculate a training RMSE and a test RMSE. I mean, I don't think it's a big hint that I'd be giving you, but they should be pretty close together. Okay, if yours vary drastically, then something's wrong. So let's calculate the training set RMSE. Okay, so I'm going to call RMSE, that's the UDF. And the first argument is the y hat. So that's, I'm just calling the predict function for the linear model, passing LM2. So that's the predicted. And then the actual is simply the response variable from the training set. So let's see what happens. I get an RMSE train is 6.9. Now this RMSE doesn't really have significance in terms of unit of measure, because I don't know what the unit of measure for a survey would be for this prestige variable. I mean, when I said if we were predicting home prices, then it's pretty clear what the units of measure are. It's dollars, and typical price of a home. You have a certain sense of it. But here, just 6.9 doesn't really have much meaning. But let's see how the the test set RMSE is. So here, I'm going to call RMSE again. Here, I'm going to be using the predict function for LM2, but based on the test set. So I have to specify new data. And then the y values, this is y hat. So the y values would simply be the response variable values from the test set. So let's run this, and we get 6.7. So see, 6.9, 6.7, they're very close. So that means, again, it's confirming that this is a pretty good model. Here's another function for calculating R squared, another statistic. So I'm not going to go over the math in this, but it's in every statistics textbook. Again, I have two arguments, y hat and y. So let's calculate the training set R squared. So I have an R squared of 83. Oh, here, let me tell you one thing. You see here in the UDF, I multiply it by 100. Now, I don't know why I do that, but to just get round numbers. But often what you see are R squared values from 0 to 1. So they're, point something. So I'm just multiplying by 100. So when I do a calculation down here and I get 83, maybe without the multiplying by 100, I would see 0.83. But the point is, you want something closer to 1 or closer to 100 as possible for an R squared. So 83 is a good R squared. There's some supplemental code, which I'm not going to go over, just some little nitty-gritty calculations here. Different ways of calculating R squared. Let's calculate the test set R squared. And I get an 84. So again, they're pretty close. And they're both good. So again, it's confirming that this is a good model. Okay, so once you have R squared under your belt, and RMSE, you would have a pretty good sense for how good the model is going to be in predicting new data. Okay, so right up to this point, all we've seen is how the model reacts to data set aside in the test set. So we can compare actual versus predicted. But there's going to be a point where we want to say, well, everything's worked out really well. Now we can break out and use the model on brand new data. And this is what organizations do all the time. As they do their due diligence and doing all the steps that I just showed you, but at some point they have to turn it loose on their customers or their users or whatever, and see how well it performs out in the wild. Okay. Before we move on to classification, though, I'm going to show you these diagnostic plots that are automatically generated for you. And it's so easy to do. All you have to do is say plot, and you give it the linear model name, and that's it. Let me show you. So let's run this. Okay, now here's the issue is notice in the command prompt, it says hit return to see next plot. You have to take your mouse and give focus to the console down here, and then hit enter. And now you see the first plot. Now I could have done the situation where I changed the graphic parameter to do like a 2x2 plot, but I found that they're too small to read very effectively, so I prefer to do it this way, so you can have a full screen plot. Okay, so what are we looking at? Well, we're looking at the residuals versus fitted plot. This is the one that we actually did manually above in the code, but this is more stylized, and you get that that red line that shows you basically how well the fit is for the model. And so what we're looking for is a total straight horizontal line. This is not a straight horizontal line, but it's close and it's reasonable. So again, it's a reasonable model. And then then everything else is the same about the about reading this plot that we identified before. We're looking for data points that center around this 0 line. Okay, so now I'm going to make sure my focus is on the command prompt, and I'm going to hit enter again. Here's our QQ plot. Again, we're looking for all the data points centered on this this line, the straight line here, and they are. That means your residuals are normally distributed, which is good, and it also highlights some observations here that you might want to consider examining closer. So like there's a row in Prestige called medical technicians. You might want to look at it to see why has it been sort of called out here. And then the third plot, scale location plot. Again, we're looking for, this is fitted values versus residuals. So again, we're looking at a horizontal red line, looks pretty good. And data points above and below the horizontal line, and it calls out any exceptional points which you might consider looking deeper at. And then one more is the residual versus leverage line, which has those Cook's distance lines. So here, let's see. Yeah, see here we have some influential data, influential observations. So here's the Cook's distance dashed lines, and here they are at the bottom. And notice that there's two data points which are identified: physicians, general managers, that are above the Cook's distance dashed lines. So these are influential observations. So you might want to dig deeper and determine why that might be the case. There's a lot more to said about this stuff. I mean, it fills whole chapters in textbooks. So there's definitely more you can learn about all this. I'm giving you the highlights. Okay, so so that's regression. So now you know how to handle any sort of prediction using machine learning that involves a numeric response variable. You just use LM algorithm. You know how to diagnose the model visually and numerically. So the other thing we need to consider is what to do about classification, which is the other type of supervised learning, where you try to predict categorical response variable values. Okay, let me clear off this stuff. Okay, clean slate here. Okay, I need to take a quick break. Give me just like 5 minutes. Heat my drink here, and I will be back shortly. Okay, I am back. So let's continue with classification. And we're going to see two algorithms now. We're going to see logistic regression, and we're going to see random forest. So let's start with logistic regression. And remember, this is the algorithm which is for predicting binary categorical variables. So any sort of variable with two options, like the spam, no spam type of situation. And remember that this is the algorithm which doesn't predict specifically response variable values. It predicts probabilities of class membership. That's how it's termed. Or the class is like the class of spam emails or the class of not spam emails. So it's just predicting probabilities of membership one of these two classes. So to demo this, we're going to use the iris data set, which we've seen before. And you might think, well, how can we do that? Because remember iris, let me just summary. Remember, the iris data set has a factor variable. That's theoretically what we're going to be trying to predict, but it has 3 levels. So how can we use logistic regression when this has 3 instead of 2 levels? So we're going to simplify the iris data set so that we can do this kind of prediction. So here's what we're going to do. We're going to create a data frame which simply pulls out from iris whether each row has a species of versicolor. So here's the result of this operation right here. So new call. So this is a data frame I'm looking at. It's got one variable. And you see the name of the variable is versicolor. This is traditionally the naming convention that you use for binary categorical variables. It's like, it's asking a question. Is the row versicolor? Like, is it? And then the answer to that question is true or false. So that means the output, as we see here, is either true or false. So it's logical. So we have a bunch of falses, and then we have a bunch of trues, and then we have more falses at the end. And that's because the way the iris data set is divided, we have setosa first, then we have versicolor, 50 setosas, 50 versicolors, and 50 more virginicas. So that's why we have 50 falses, 50 trues, and 50 more falses. And now I'm going to use a cbind to, attach this new column onto iris. And I have new iris. Here's new iris. So see, here's that the new binary categorical variable I just created. It's part of the data set now. And now I'm going to use the same code. Remember, I promised that you can use the same code to split training into training and test, no matter what project. Well, here I'm using it for a totally different algorithm, totally different data set. but it's the same code as we saw earlier for regression. So let me just run all this. So now I have training set, train iris, test set, test iris. It's as easy as that. And I'm going to use logistic regression for predicting is versicolor. So instead of predicting species, which I know I can't do because it's got 3 classes, I'm going to predict this one is versicolor. So it just has 2 classes. And so I call the GLM algorithm. I specify the formula. So the formula, again, the response variables on the left is versicolor, tilde, sepal width on the right. So I'm doing a single predictor. I'm just curious. I want to see, hey, can I predict whether the observation is versicolor based on just the sepal width variable? I don't know if this is going to work out or not, but it's the kind of test you often do as a data scientist. So I specify the training set here in the data argument. And then this is very important, family equals binomial. So this is how you tell GLM to do logistic regression, because GLM does other things. So you have to specify this. I'm going to train the model, display the model, and you'll find that every algorithm has somewhat different output when you display it. Do a summary, and it does have the coefficients matrix, does have p-values, asterisks, but it includes other statistics down here which we didn't see for linear regression, and every model is like that. Okay, now let's let's do our plot of predictor versus response. Just want to scatter plot to see what we're dealing with. So here I say plot, training set, predictor variable, and training set, response variable. Okay. So this is an interesting plot, because we see that on the x-axis we have our predictor variable. So sepal width ranges from 2.0 to 4.7 something, and there's values all way in between. But on the y-axis, the predictor variable, the response variable, it just has 2 values, 0 or 1. So 1 is for all the falses, 0 is for all the 0 is for all the falses, 1 is for all the true values. So they're automatically coerced into an integer value. So that's why they're, we see a discrete separation. There's nothing in between. It's either, trues down up here or falses down here. So no real surprise. So the only concern is now how are we going to use logistic regression to predict probabilistically whether it's true or false. True means the observation is versicolor. False means it's one of the other two species. So here's how we can visualize what we're talking about. we can start with the predict function for logistic regression. I say I want to do a predict function for this GLM1 model, and I want to predict well, I want to use this data sepal width, and I want to predict the response variable values, which is, you know, the true, the false, or is versicolor, because that's how the model was trained. And I want to add this. I want to render this analysis using a curve function from base R graphics, and I want to add it to the scatter plot. So here's my curve. So the curve is sort of an S-shaped function. Sometimes it's called a sigmoid. And it shows what's referred to as a dichotomous nature of the logistic regression algorithm. It's predicting, in this case, between two values, true or false. So in this case, the y-axis here is versicolor, shows values of the predicted is versicolor between 0 and 1, because it's probabilistic. It's saying what is the probability of a certain, you know, sepal width data point versus the true and false value of its versicolor. So you can kind of like play with the plot a little bit. You can say, well, let's take a sepal width value of 3. Okay, so it's 3.0. And you mentally draw a vertical line up to the curve. So right about here. And then you mentally draw a horizontal line over to the y-axis. And you notice that this lands on a value like maybe say 0.3. So that means that if the predictor value for sepal width is 3.0, there's a 30% probability of the observation being versicolor. Whereas, let's say, take a value of sepal width 4.0. So here's 4.0. And you do the same process of drawing these imaginary lines. And look at this imaginary line. It's almost 0 probability. If sepal length is 4, 0 probability of being a versicolor row. And the highest you get is up here with very low values of sepal width. You might get up to 80% probability. So that's how you read a result from logistic regression. It's always probabilistic. Now here I'm going to try to use the trained model to predict, you know, so just some random sepal width value. So that's my predictor, right? So I'm going to say, well, let me use the model. Let's say my sepal width is 2.4. What is the probability that the observation in iris is going to be Versacolor. So let me create a tiny little data frame here. And then we use this, this function is called predict.glm. You pass it the trained model, you give it the value you want to use as a predictor. You want to produce the response variable, predict the response variable value, and what do you get? 67. So 2.4. So 2.4 is around here. You go up to the curve. You go back out to the y-axis, and yeah, the value is somewhere around here, 6.7 or 0.67. Okay, now let's extend out this example to use multiple predictors. So here what I'm going to do is I'm going to say I want to use, let's see, yeah, all 4 of the variables in iris to predict whether the result is Versacolor. So here what I'm doing is I'm creating a formula object. So I can do that. I can just stuff a formula away in an object variable. And then use it here as the first argument. So calling GLM in this case is exactly the same as I saw before. It's just my formula has been expanded. And now I can look at a summary. Here's my coefficients table. So you see, like sepal width, none of these are very good at predicting a particular species, which might be surprising. I mean, it's it's a life sciences data experiment, dealing with flower species. And you would think that the dimensions of the flower itself would be useful in predicting the species, but this is saying not so much. The p-values are pretty bad, with the exception of this one. So here's my coefficients. I can also do a summary on the coefficients, extract the whole table, the whole matrix. And here is how I now bring in the use of the test set. And you always do this after you've trained the model on the training set. So GLM2 was trained on the training set. Now I use the predict function for the algorithm. This time I'm using on the test set. And my output is a bunch of probabilities. The way you read this is like they're all values between 0 and 1. So this just says 25% likely to be Versacolor. And just scanning this list, Here's one that goes almost to 70% probability. Here's a 72. None of them are very high probability. Even the ones in the test set that are versicolor. So, but let's see how this sort of works out. So here is a strategy that involves setting a threshold or a cutoff value for your logistic regression. This is something you have to do all the time for logistic regression, because all it's doing is giving you probabilities. So you have to say, well, okay, let's say anything above this threshold, I'm going to view as a match, a class match. Anything below, I'm going to say it doesn't match the class. So here's where I do that. I have an if else, and I just say, if any value in my probability vector, for my predicted probabilities of class membership, if it's greater than 0.05, then I say, all right, it is versicolor. If it's less than 0.5, less than or equal to, then it's not versicolor. So here's all of my, zeros and ones, trues and falses. So I can use this this function, or this expression, I can use to come up with a test error rate. So you always want to minimize any sort of error. That's what you're working towards. I mean, if you can minimize it to 0, that'd be great, but you never do that. This one is minimized to, well, the test error rate is 28%. So that, I don't know, it's not horrible, but it's not that great either. And this code right here, you can use directly in the solution of homework 2 in a second question on logistic regression. I'm sorry, homework 3 on logistic regression. And so this test error metric, this is called a misclassification error rate. So this error rate was 28% based on using all the predictors. If you only use, I just happen to try this out, if you only use sepal width as the predictor, so one predictor, you get a lower error rate, which is interesting. It's like the other predictors are kind of extra baggage. It's not helping out. But this is the type of thing you find when you're doing experiments like this. Okay, so with classification problems, you're always calculating the misclassification error rate. Another thing you always do is doing the ROC curves and calculating AUC, the area under the curve value. So I showed you on the slides what a good ROC curve might look like. And I also mentioned that the higher the AUC value, the better. So here's what I'm going to give you. I'm going to give you a chunk of code here. It's a UDF called CalcRoc. I'm not going to explain it. You can dissect it and figure out how it works. But at this point, we don't really need to know how it works. We just need to know how to use it. But it's built using stuff you already know. So I'm just going to define this. Oops. Just try it this way. Okay, so I got the whole thing defined. So now we have a function called calcroc. And let's see, what does it take as arguments? It takes probabilities. So those are predicted probabilities and actual, or AKA known truth, ground truth, sometimes people call it. And then you can also, there's a third argument where you can give it a name. You can give the rock curve a name to match the name of your model. That's all. Okay. So to utilize the rock curves, I'm going to have to define dplyr and ggplot2. And for convenience, I'm going to attach iris so I don't have to repeat the iris name over and over in different commands. So here, to start this off, I'm going to use a dplyr function filter to produce an iris data set, or a reduced iris data set that only contains virginica and versicolor. So here's something called iris small. So it has everything that iris has, except it carved out all of the carved out the setosa variable. It only contains virginica and versicolor. So it's 100 rows. So now that it only has like 2 possibilities, I can use logistic regression on that, because there's just it's a 2-class response variable. So I can say species now only has 2 classes, and I want to, so that's my response variable, and I want to use petal width as the predictor. I'm pointing to iris small. So now I have a trained model. So now I want to create a rock curve. So I call calcroc, and the first argument is probabilities, and so probabilities of class membership. So I just give it the fitted.values item in the GLM1 model. And then known truth, the actuals, is simply the species variable from iris small. So what this produces, see over here, is a data frame. And remember on the slides where I showed you what constitutes a rock curve? These values, true positives, false positives. So that's what calcroc yielded, the 2 data points for a rock curve. See, the rock curve is just a data frame that's being populated by calcroc. Now what I'm going to do here is I'm going to produce a few other models based on the same data set, just different predictors, and yeah, just different predictors. Because what you typically want to do on a ROC curve is you want to do more than just display the ROC curve, although that's good. You want to have, let's say, a number of choices to see which ROC curve is better. And so the way you do that is you have different models with different set of predictors. So the first one I had was the predictor was pedal width. Now I want to do another model where the predictor is sepal width. So I'm going to do that, and I'm going to train the model. Then I'm going to create a new ROC curve. So I have a second data frame. Now I'm going to do another model. This was pedal length is the predictor. Calculate a third ROC curve. And then the final model will be, let's see, 1, 2, 3, 3 predictors. And I create a fourth ROC curve. Okay, so four ROC curves now. And what I'm going to do here is I'm going to use ggplot2 to display all 4 ROC curves, representing 4 different models. So my hope is I can use the ROC curves to tell me which is the best model. Oh yes, good old ROC curves. Look at that. There we go. So remember I told you on the slides that the best ROC curves are always the ones that go the highest and hug that upper left corner the tightest. And so I can see that of these 4, the red one is doing the best job. I have a purple one here, which is doing a very poor job. It's almost, no better than flipping a coin. And then there's 2 others which are sort of crossed over. And by looking at it, I can't really tell which is better, one or the other. So the red ROC curve happens to be the combined model. That means the 3 predictors. Maybe no surprise. The 2 shades of green here represent models based on pedal length and pedal width, and the bad one here is based on sepal width. So this has helped me, right? It's helped me to choose the winner, but maybe I want to know which is second place, third place, whatever. So, and maybe your list of ROC curves is denser than this. Maybe you have like half a dozen or maybe 10 ROC curves you're looking at all at once, and maybe you can't discern which is better just by looking visually. So you need something numerically. So let's calculate the area under the curve. So I'm going to use these I'm going to use these dplyr expressions here to calculate AUC. So for example, the AUC for the first rock curve, which is the winner, is 0.9888. Now, I said that the largest AUC, the better. So AUCs go from 0 to 1. So this is pretty close to 1, very close to 1. So this is an excellent AUC value. But let's look at them all together. So I'm going to do an R-bind on these 4 data frames. So I have rocks. So rocks has 400 rows now, and it's just, they're stacked together. All of the rock curve data stacked together. So what I'm going to do is I'm going to use another more detailed dplyr expression here. I'll let you dissect it. And the purpose of this will be to calculate the AUC for each of the rock curves and deliver the results. So here's my results. So here's the combined AUC is a 0.997. That's even better than the one we saw a moment ago. Petal length and petal width. Look at that. They're separated by 0.001. So there was no way I was going to figure that out by looking at the rock curve visually. I can only do that by looking at it numerically. And then this terrible one is AUC is 0.7, so that we know that's bad. Okay, so those are rock curves. Now, rock curves can be used for any classification problem. So when you're trying to figure out how good a classification problem is, you're doing rock curves and you're calculating the misclassification error rate. Those two things. And also AUC. So you have a lot of tools to figure all this out. So now we just have to look at another algorithm. Random forest. So random forest is a significant innovation in machine learning. It was developed a number of years ago, decades ago, actually. And it's for quite a while, it was the favorite. More recently, like boosting methods have surpassed this in popularity, but it's still pretty good. So let's bring that into memory. We're going to use iris again. We're going to split the iris data set into training and test using the same code as we saw before. And now, since random forest can predict multi-class response variable values, we can specify this directly. We could say formula, species, tilde, and then period, meaning all the other 4 predictor values. We train it on train iris. And then we specify one or more so-called hyperparameters. So many of the more sophisticated machine learning algorithms have a series of hyperparameters. And herein lies the issue is for you as somebody just starting out with machine learning, it's like, how do you figure out these hyperparameters? Well, you really have to know how the algorithm works to really be confident in your use of hyperparameters. And that's where I'm saying you should, at some point, you've got to learn the theory and the mathematics behind these algorithms so you can do a reasonable job of selecting hyperparameters. Otherwise, you're just going to be like copying other people's code. Like you'll probably copy my code. Entry 500, mtry, I mean, which is fine. Importance equal true, whatever. But at some point, in order to get optimal results, you'll need to know how to configure the hyperparameters yourself. And there's a lot more to learn because there's a lot of hyperparameters. Some algorithms have many, many, many hyperparameters. Each one is very nuanced. And the interactions between parameters are important. So anyway, let me train this model. Okay. So now I have the trained model RF. And as I may have mentioned in the slides, depending on the size of your data set and the number of your predictors, training random forest can take a while. So for your class project, you might, depends on the speed of your computer, but it could take 5-10 minutes to train it. So don't get impatient, it's working. Okay, so now I've got a trained model. Let's use the trained model with the predict function on the, so here's the trained model, argument 1, here's the test set. For random forest, you have to specify type equals class instead of response, like you did for logistic regression, and you get output. And so here's what's in this prediction vector. So unlike logistic regression, which delivers probabilities, random forest is predicting specific species. So remember, in the test set, you've got response variable values. Those are the actuals. And then now you have a set of predicted response variable values. So your job now is to compare the two to see how good the model is. And one easy way, and this is another tool that you have for classification, you can use a confusion matrix, which it allows you to visualize the actual versus predicted response values, but in like a matrix form. And you just use the table function for that. So you say table, one variable is prediction, the other variable is the actual species, and here's what it looks like. So remember on the slides, I said what you're looking for is most of the numbers to be on the diagonal line. So the diagonal line is here, 17, 23, 19. There's one straggler. This is a misclassification, but only one. So that means that random forest is very capable of predicting species based on the data from the iris data frame. Not bad, very predictive, but this is how you verify it. Here's another way of visualizing this. I'm going to use a package called Gmodels. And it has a function called cross-table. And it's kind of the same thing. As a table. Just a different way of looking at it. Let's calculate the misclassification error rate. So here is an expression to do that. It's basically just comparing all of the predicted species from the test set, the actual species to the test set. I'm tying it together using a logical expressions not equal. So it's going to generate trues and falses. So I put that in a sum function because it'll sum up all the trues as ones and all the falses as zeros. And what do I do here? I divide it by number of rows. And I come up with a very small error rate. We're always looking for small error rates. So this one is only 1.6%. That's great. Love to have that error rate. It's never going to be zero, but it's pretty small. Here's, by the way, here's all the, in my trained random forest model, there's a whole bunch of statistics that were calculated. And let's just see. See, RF is a list of 19 elements. So this was, I was saying like last week is that, or last lecture is that you should get very good at random forest after this class. Just take some time and learn everything you can about it. In particular, learning about what all these calculated elements mean and how you might use them. Some of them not so much, but others, sure. In fact, there's one I forgot to mention here. Let me just show you this importance argument. I always specify this, even though it slows down the training, so it'll run even slower. When you specify this one, and that means that what it's doing is it's causing random forest to collect statistics to determine how important each feature variable is to the predicting of the response variable. And that's a nice asset. I think it's worth the trouble. That's why I always do it. And fortunately, when you do it, when you do the variable importance argument, you can do this. You can run this diagnostic plot, var imp plot. And here's what you get. So this is telling you over, like, let's take this left side. Here's all the predictors. And what you're looking for are data points in this plot that are as far over to the right as possible. So here we see petal length is all the way over to the right. Petal width, very close to the right. Sepal length, not at all over to the right. Sepal width, not at all. So what this means is you can now go back and rerun the random forest algorithm with just these two predictors, and you'll be fine. You don't need all these. Like once I was doing a project, and my training set had I think it was like 32 variables, so a lot more than we've seen in this class. And I did a variable importance plot, and it was really interesting because there were only 4 of the 32 predictors that were on this right side. The others were like lined up all the way on the left edge. And that is saying random forest has determined that, you know, these 28 other predictors have, you know, very little ability to predict the response variable. So I went back and reran it, and sure enough, I didn't need all those other predictors. So it's interesting that you can get a machine learning algorithm to help you use the machine learning algorithm. I think that's kind of wild. So, but very, very helpful. Okay, we've done it. We went through the whole code base. Now, let me just say that everything that you've learned in this segment of week 9 is you now can do the first 2 problems for homework 3. You can do the entire class project. And the only thing that's missing now is unsupervised learning, which is the subject for week 10. And that's things like clustering and stuff. Once you see that, then you'll be able to do the 3rd question on homework 3, and you'll be done with all the coursework for the class. So you're in a good spot right now for moving forward. All right, so let's see. For the 2 of you that are here live, I appreciate it. And for the rest, I'll see you all in class next week.